Okay, so welcome to the afternoon session, and the speaker now will be Koji Azuma, and speaking about do black holes store negative entropy? Okay, please.
Thanks for the introduction. And first of all, I'd like to thank the organizer for giving me opportunity to give a talk here. My name is Koji Azuma. I work at NTT Basic Research Laboratory in Japan. And today, the title of my talk today is Do Black Holes Store Negative Entropy? This work was done with my collaborator, Dr. Satya Subramanian and Go Kato. Before starting my talk, I would like to thank them sincerely. Let's start. And today, I want to talk about the so-called area law for black hole. More precisely, today, we would like to apply quantum information theoretical viewpoint to black hole physics to resolve a paradoxical nature given by this area law for the black hole. To achieve such a goal of my talk, starts by briefly reviewing the key concept of the quantum information, and then I enter the brief review on the black hole physics. And after that, I want to introduce some inconsistency between quantum mechanical viewpoint and black hole mechanics. And finally, I will give us our idea to resolve such a paradoxical nature of the something. Okay. My talk starts by briefly reviewing the key concept of the quantum information. Okay, actually, the quantum information theory is a pretty simple theoretical paradigm in some sense, because the quantum information theory is regarded as just a mathematical framework based on the four postulates of quantum mechanics. Quantum mechanics is based on just the four postulates. The first postulate is talks about the description of the physical system and the physical state. In the quantum mechanics, as you know, that a physical system is associated with Hilbert space in the quantum mechanics, and its state description is corresponding to the normalized vector in the Hilbert space, or a ray, is more precisely. The second postulate is just talks about the time evolution. The time evolution of the wave function or quantum state follows the Schrödinger equation. Such a Schrödinger equation can be written by this type of form, where the quantum state at some different time are connected by unitary operator. The third postulate talks about the observable. And the observable means like a momentum or position in the physics. Such observable is associated with the self-adjoint operator in the Hilbert space. Since a self-adjoint operator is always diagonalized, therefore, without loss of generality, such operator can be written in this spectral diagonal spectral decomposed form. Here, that AN represents the eigenvalue. Eigenvalue represents the possible outcome, which could be obtained if we perform the corresponding measurement for the system. The eigenstate represents the state, such that if we apply such a measurement for the system, this eigenstate returns the outcome, always AN here. And in general, that if we perform such a corresponding measurement to the general state, psi, ket psi, in this case, that the probability to getting the specific outcome AN is represented by this equation, which is called Born's rule. The fourth postulate talks about the composite system. If the physical system A is associated with Hilbert space HA and the physical system B is associated with Hilbert space B, then the composite system should be described by tensor product of the Hilbert space. This is just a four postulate. Why I introduced that this postulate is here, this is related with I want to introduce the concept of the quantum information. Namely, the goal of the quantum information theory is to answer what kind of information processing is possible by combining these four postulates. This is the main concept of the quantum information theory. And as a result, we have already known how to describe a state in general. A state of a system A, including classical one, is described by a density operator in general. Density operator is just a mixture of the quantum state. Here, the Pi represents the probability distribution. Ket psi represents the quantum state. Therefore, the density operator is associated with ensemble of states. And this situation described by this type of cartoon. Here, we assume that some source emits the quantum state of psi with probability Pi. This situation can be described by using density operator. This is this is like a description given by quantum mechanics. For instance, if the density operator is a pure state, then of course this formalism reduced into the normal quantum mechanics which appear in the normal textbook. On the other hand, if the density operator is a mixture of orthogonal state, in this case, we also assume that just assume that all the possible operations for such a system are also diagonalized in the orthogonal basis. In this case, this density operator, namely mixture of the orthogonal state, is regarded as classical state in your community. This is because all the phenomena in this situation can be explained by using conventional information theory. More precisely, in the conventional information theory treats this type of paradigm. Namely, in the classical information theory, source emit alphabet I is probability Pi. We apply the classical operation, which is governed by the transition matrix. Then such a classical operation outputs the alphabet J. This is the formalism of the classical information processing. Therefore, as long as we have a premise that all possible operations are diagonal in the orthogonal basis, and the density operator is a mixture of the orthogonal state. In this case, the quantum information theory is equivalent to the classical information processing. Therefore, please notice that therefore the quantum information theory is a broader paradigm than classical information theory. Okay, then I also want to introduce the so-called purification. This is a very important notion in the quantum mechanics. And the quantum mechanics always allows us to regard a quantum system A in a general mixed state in general, but a density operator as a subsystem of a larger system AE in a pure state psi. Here the pure state AE, if we take the partial trace over system E, in such a case, reduced density operator for system A is equivalent, equate such a reduced density operator. What is this concept? Like if some observer has a system A in a mixed state, in such a case, we can always imagine the existence of purification partner somewhere in our universe. Therefore, even if we have some mixed state, and such a mixed state can be regarded as like a larger subsystem of a larger system in a pure state. As an example for this type of density operator, we can always consider this type of purification as an example. Therefore, anyway, according to quantum mechanics, if a system is in a mixed state, there is a purification partner somewhere in our universe. This is associated with why the many world interpretation still possible in the quantum mechanics formalism. Therefore, in principle, quantum information scientists, maybe universe should be in a pure state because of thanks to the existence of this notion of the purification. And I also introduced a very basic idea called Shannon entropy. Shannon entropy is a very important role plays a central role in the classical information theory. Shannon entropy is defined for any probability distribution. The Shannon entropy is defined in this form. By using such a Shannon entropy, we can define the mutual information and the conditional entropy as follows, like this form. Please notice that these mutual information and conditional entropy are both positive quantity. Therefore, we can write Venn diagram to summarize this situation for the bipartite system. Actually, in the classical information theory, that each term has each operational meaning in the context of the classical communication between Alice and Bob, etc. This is an important conclusion given by classical information theory. And such a theory is called nowadays a Shannon theory in our community. And such a Shannon theory is now generalized as the quantum version of the Shannon theory. In such a Shannon theory, we normally use the von Neumann entropy as a generalization of the classical Shannon entropy. Such a von Neumann entropy is defined for any density operator. The definition is described like this form. By using von Neumann entropy, the mutual information and the conditional entropy are defined by this form. Namely, that these definitions are pretty analogous to the classical ones, where we just define the G's quantity by replacing the Shannon entropy in the classical world with the von Neumann entropy. Please notice why this definition is adopted in our community. Suppose that the rho AB is in a classical state. Namely, if the density operator is rho AB is a classical mixture of the orthogonal state, then all the above quantity are reduced into the classical ones based on the channel entropy. Therefore, these quantities are regarded as a generalized version of the mutual information of conditional information entropy or fundamental channel entropy, etc. Therefore, again, I want to mention about the quantum information theory is broader than the classical. And however, in contrast to classical cases, in quantum cases, we cannot write a Venn diagram because the conditional entropy could be negative. Okay, and for example, this can be easily understood by considering this example. Suppose that the low density operator rho AB is in pure state. In this case, that the fundamental entropy for the system AB itself, therefore the conditional entropy becomes a minus SB. This is in general, this could be negative. Therefore, in the quantum world, conditional entropy becomes a positive and negative, depending on the situation. Therefore, by just reading this situation, one might notice that maybe conditional entropy might look to be related with entanglement. This is true. This is true. Indeed, minus the conditional entropy called the coherent information is associated with entanglement. Coherent information is defined by just a minus the conditional entropy. Okay, and however, the coherent information is associated with entanglement, but this is not exactly an entanglement measure because the coherent information could increase under local operation and classical communication. However, that still coherent information is associated with entanglement. Actually, the positive coherent information has operational meaning, clear operational meaning in the context of the quantum state merging protocol. Quantum state merging protocol was introduced in the 2005 by Horodeski et al. Here we consider the following situation, namely Alice and Bob have a copy of the density operator AB. As I said, in the quantum information theorist, we can always imagine the purification partner somewhere in your universe. Therefore, this psi A, we can regard the system E as just a purification partner of the density operator between Alice and Bob. Then we assume that Alice and Bob share such a copy of the state, psi A, B, E, n copies of such an initial state. Then Alice performs some measurements after performing the unitary operation, which is chosen by at random. After that, Alice performed the projective measurement. Such outcome is sent to Bob's side. Bob performed some correction operation. Then, in such a case, Alice and Bob arrive at this type of situation. In this situation, namely by using one-way LOCC between Alice and Bob can transform this state into this form. Here, the output is regarded as the following. Like Alice's state A is merged into the Bob's side. In addition, Alice and Bob obtained a beautiful maximally entangled pair here, namely many number of copy of the Bell state here. The coherent information has a clear meaning in this quantum state merging protocol. More precisely, the ratio between M and N, M over N, M represents how many number of entangled Bell pair are obtained through this protocol. N represents a number of copy of the initial state. The ratio between M over N approaches the coherent information in the limit of the N goes to infinity. Therefore, this coherent information is associated with how many number of Bell pair can be distributable by performing some protocol between Alice and Bob. Okay. Question? Okay.
I just like to understand can you explain this protocol without introducing an environment? And how does one do that?
Actually, this is the definition. Like why we introduce a purification partner. The goal of this one is a quantum state merging. The goal of the quantum state merging is just to merge the Alice's system into Bob's side with keeping coherence with the environment. This is the goal of the protocol itself. Therefore, from the initial point, we implicitly assume the existence of environment system. The goal of this merging protocol is merge such a Alice's system into Bob's side, keeping quantum coherence with such an environment. That's why this is like an assumption. And so if we forget about the environment, actually that such a generalized quantum state merging is sometimes considered in our community, but this is pretty difficult problem actually.
Just a very quick follow-up then. But nevertheless, the quantity is independent of the choice of purification, correct?
Yeah, actually the purification always has a freedom. Like if once we are given some density operator, we can imagine the purification partner. Even if we apply the unitary operation for the purification partner, the same purification. Therefore, even if we perform some unitary operation, of course the state description is a bit different, but the distillable entanglement doesn't change.
Sorry, I got a bit confused. So you say that this conditional entropy has an operational meaning, namely that it counts certain number of bare pairs. But does that mean that the conditional that the coherent information counts this number of bare pairs? Does that mean that the conditional entropy is always negative?
No. That's a nice question. Like as I said, if we consider like this type of classical state case, all the quantity is reduced to the classical conditional entropy of mutual information. Therefore, that the conditional entropy in such a case becomes positive. But this protocol has works only when such a conditional entropy, namely initial state, if this protocol works when this psi
okay, so this certain type of state, I mean that this conditional coherent information counts number of bare pairs.
Yeah.
That's the statement. I see. Okay. Yes.
But it's not that you need to spend a couple of years to do positive, you can get positive in terms of pairs, but at the end of the process.
Thank you. Yeah. Okay. And I go proceed further. Okay. And therefore, this is very important result in your community. Okay. And I also want to mention about difference terminology between the quantum information theory and black hole physics, for example. From our viewpoint, like if the density operator is a maximum entropy ensemble, such as a canonical ensemble state, or such as a microcanonical ensemble state, its von Neumann entropy is reduced to the coarse-grained entropy, which satisfies the thermodynamic relation, etc. Namely, from our community, von Neumann entropy is just a general measure for the which is defined for arbitrary state. But in the black hole community, maybe sometimes this entropy is called fine-grained entropy or etc. But from our viewpoint, just like we normally use a von Neumann entropy as a measure of any kind of state. And if the density operator has a restriction such that such a density operator should be a maximum entropy ensemble, in such a case, its von Neumann entropy is reduced into the coarse-grained entropy. This is our viewpoint. Okay? Therefore, here I want to stress that von Neumann entropy is like a perfectly generalized version of any kind of entropy in principle. Statistical mechanical entropy or classical Shannon entropy also, right? This is I want to mention why I review this type of basic stuff in this conference. Okay, what I want to change my topic a little bit because I have already introduced our concept in our field. What I jumped into the brief review of the black hole physics. Maybe this is well known in this audience in this workshop, but I want to make a brief review on the black hole physics. From my understanding, the black hole mechanics start by finding given by Bardeen, Carter, and Hawking in the 1773. Bardeen et al. Considered just a general under classical general relativity. They derived a so-called first law for a stationary black hole. This is essentially just an energy conservation law for black hole spacetime. The change of the mass of the black hole should be associated with the change of area, change of the angular momentum, and change of the charge, etc. Therefore, this is just a fast energy conservation law for black hole spacetime. And as well as the Bardeen et al. Provide also second law for any classical process except for Hawking radiation. Namely, as long as we consider classical process such as black hole merging or etc., the area of the black hole monotonically increase. At the same time, they wonder whether that maybe these first and second law looks very analogous to the first and second law for thermodynamic physics. Therefore, that in their paper, they wonder whether that maybe first term of the right-hand side in the first law may be associated with temperature times entropy, change of entropy. But they were at that point very conservative. Namely, they just consider under classical general relativity. Therefore, at that point, temperature should be there because the black hole seems to absorb only in the classical process. And at the same time, consideration the Gedanken experiment was given by Bekenstein. The Bekenstein considered the following simple Gedanken experiment. Bekenstein just threw the entropic particle to the black hole. Of course, the black hole absorbs such a particle, and then such a particle disappears outside the black hole. Then Bekenstein asked us, if black hole has no entropy, namely if the pure state, entropy disappears from our universe. Namely, for example, if we find some entropic particle outside the hole, we just throw everything to the black hole. Then we can delete entropy outside the hole. Therefore, which is incompatible from our universe. Therefore, which is incompatible with the second law of the thermodynamics. Therefore, Bekenstein also maybe conjecture that maybe black hole should have entropy. But the entropy should be associated parameters appearing in the first law because of the no-hair conjecture for black hole. Therefore, he argued like maybe if the black hole has entropy, entropy should be associated with the proportional to the area. But he cannot determine the proportional constant temperature TB here. The temperature was determined by actually Hawking radiation, Hawking paper. And Hawking finds that Hawking radiation, black hole radiates something, thermal radiation from the hole. Okay, then Hawking considered focus in the first paper, first focus on the Schwarzschild black hole. In this case, first law of the black hole mechanics is simply written by this type of form. Namely, change of the mass is associated with change of the area in this case, because the Schwarzschild black hole has no angular momentum and charge. Then Hawking expands the semi-classical theory, then by considering that Schwarzschild black hole spacetime described like this form. In this spacetime diagram, the pink line represents past infinity, orange line corresponds to future infinity. Green line corresponds to light cone, which becomes the event horizon after black hole has made. And the Hawking focus on the possible trajectory, which passes near the event horizon and finally comes back to the future infinity. This is just a massless color boson he considered. Then, for such a possible trajectory passing near the event horizon, Hawking finds that this trajectory creates an entangled pair, which is now regarded as a two-mode squeeze state in our community. Okay, even starting from the vacuum state here, namely, even the possible trajectory start from the vacuum state, by passing through the event closer near the event horizon, this entangled pair appear. Namely, the observer at the future infinity receives some thermal radiation from the black hole. And the purification partner maybe falls down into the black hole. Since from the observer at the future infinity or spatial infinity observer, the black hole inside the black hole has only negative energy spectrum, such a negative H minus, particle H minus should have a negative energy spectrum also. Okay, then what is a surprising fact, like this two-mode state case, the reduced density operator, this H plus particle is a proportional Gibbs state. Gibbs state only has a one parameter associated with temperature. And by considering this type of quantum field theory over curved spacetime, he concludes that this temperature of the thermal Gibbs state of the H plus is in the kappa b over 2 pi. Okay. Then he determines that the temperature of the radiation from the black hole. Besides, Hawking regards this radiation temperature as the temperature of the black hole. Namely, TB appear in the as this analogous relationship as an unknown parameter. However, such a parameter now is determined by regarding thermal radiation temperature is equivalent to the temperature of the black hole. As a result, they arrive at the so-called Bekenstein-Hawking equation. Okay. Then the fact that someone receive a positive energy particle from the black hole, therefore that the mass of the black hole should decrease. According to the first law of the black hole mechanics, of course, that the area of the black hole should decrease. This is like a story understood even by quantum information scientists like me. Okay? And next, I want to introduce an inconsistency proposed by some quantum information scientists in our community. Okay, then this is a conventional story, but from quantum information scientist viewpoint, this looks strange in the sense that actually that as Hawking suggests, vacuum state is transformed into two-mode squeezed state. However, the H plus and the H minus is in a pure state. In this case, the entropy of the H plus is equivalent to the entropy of the negative energy particle falling into the black hole. Therefore, the entropy should be positive value, even for such a negative energy particle falling down into the black hole. Therefore, if we seriously believe the Bekenstein and Hawking equation is correct, of course, some entropy or dimensionality of the black hole increases through the generation of the Hawking pair. Therefore, the entropy increases, black hole entropy should increase, which means that the area of the black hole increases according to the Bekenstein-Hawking equation. Therefore, these are incompatible, which was mentioned by Brownstein et al. In our community. Okay, what is a key observation here from just a quantum information theoretical viewpoint? Okay, let's go back to the consideration given by Bekenstein again. Bekenstein consideration is very simple, like just a Bekenstein for the entropy particle to the hole. Of course, as I said, in the quantum mechanics, we can always imagine the purification partner somewhere in our universe. Therefore, the purification partner exists somewhere outside the hole. Therefore, the Bekenstein's Gedanken experiment is regarded as just an entanglement generation between the black hole and outside. And on the other hand, what is the Hawking radiation? Hawking radiation argues someone at a future infinity receive a thermal radiation, which is mixed state. Therefore, we should imagine the existence of purification partner even for this state. Such a purification partner actually appear inside the hole, which is proposed by Hawking, right? Therefore, purification partner appear inside the black hole. Therefore, what is the question here? Anyway, from the microscopic viewpoint are not so different between the Bekenstein's Gedanken experiment and the Hawking radiation, because anyway, entanglement generation between the black hole and the outside. However, the action for the area are entirely different. Namely, in the first Gedanken experiment, Bekenstein argued the area should increase. On the other hand, Hawking radiation area should decrease. Therefore, from the microscopic viewpoint, anyway, both process talks about the entanglement generation between the hole and the outside. However, the change of the area are completely opposite.
Just to make sure, are you talking about the physics before the page time or after the page time?
Okay, page time is pretty okay.
Yeah, so before the page time, I mean,
the
two notions are different, right?
Yeah, in the case of page time, after page time, people regarded as a purification partner also start to appear outside through the island, etc. Right?
Yeah.
Okay, and as I said, just before the page time, at least this type of situation. Okay.
Okay.
Therefore, you can
in that case, this black hole entropy and this, I mean, that the entropy of this actual QFT state would be a different notion. So for me, it seems like there is no inconsistency.
Just like this is not just an intuitive discussion. So later.
Okay.
yeah, phase is a bit completely different formalism. So let's talk about it. Okay, then in this case, okay, but you may misunderstand black hole physics. Of course, Wittgenstein, someone argue maybe entropy appearing in the Wittgenstein-Hawking equation should represent a coarse-grained entropy. Okay, such a person says such a thing. Namely, since a black hole should be in a microcanonical ensemble, it should follow the thermodynamic relation described like this. Therefore, once you admit the decrease of the mass of the hole by a Hawking radiation, the coarse-grained entropy should also decrease. Hence, there is no problem. What are you considering for something like that? There is no paradox here. However, please notice, even in this case, I think there is a paradox if we believe the Hawking pair creation picture is correct. Namely, according to Hawking's formulation, this H minus is the negative energy bosons, right? Therefore, the H minus is a bosonic system with an unbounded negative energy spectrum. On the other hand, black hole should have also positive energy object, because otherwise that the black hole's mass should be positive. Therefore, the black hole in some sense should have a positive energy particle also. Therefore, the black hole is regarded as just not only have a positive energy spectrum particle, but also negative energy boson. In such a case, we question like how to regard the hole B as a statistical mechanically stable system. Or microcanonical, in this case, microcanonical ensemble is not well defined because of that. In this case, we have an unbounded energy spectrum boson inside the hole. Therefore, we want our strategy is just we just do not want to change the Hawking's pair creation picture. Okay, our key idea is the following: instead of throwing out Hawking's pair creation picture, we explored possibility to keep the picture Hawking's picture as it is, by utilizing the fact that Hawking radiation is special in the sense that it uniquely generates unusual negative particles inside the hole. Okay, therefore, we want to modify the Wittgenstein-Hawking equation rather than believing that okay, this represents coarse-grained entropy or etc. Okay.
Actually, if we, usually when we talk about thermodynamics of black hole and evaporating black hole, we have this area term as you write it AB, but also we need to add matter contribution.
Yeah, generalized.
Yeah. Some of them, then it always increasing.
Okay.
Even though area, but still, so, but I just wonder why you are only looking at area.
Just like we focus on this quantity only, but of course I know that in the black
SB actually correspond to area plus I think also
other term.
Yeah. So then I think no paradox. Or
yeah, perhaps. Yeah, this is just I focus only on this SV represents just some entropy, really information theoretical entropy. Of course, there is many interpretation what is meant by and S here, right? But in this talk, I just focus on the SV, just represent the fundamental entropy. Then maybe fundamental entropy may be reduced into the coarse-grained entropy if we consider the state B.
Your definition of SV is equal to area.
Yeah. This is like a
This is a
starting point. Yeah, starting point. Therefore, if we change the left-hand side, maybe such a paradox may not appear. Okay, and therefore, we want to change the Wittgenstein. We normally, more precisely, we would like to really modify the Wittgenstein-Hawking equation to keep the Hawking's pair creation picture as it is. Okay. To achieve such a goal, we made two assumptions. Black hole B is actually composed of not only positive energy particle B plus, but also negative energy particle B minus. B minus is like generated by just passing through the Hawking radiation, because the Hawking pairs, Hawking radiation generates a negative energy particle inside the hole. Such a particle contributes to increase the system size of B minus here. Okay, B plus represents some normal matter inside the hole, such as mass. That's why black hole's mass becomes positive. Okay. Therefore, our formulation is like this one. In contrast to normal theory regards the black hole follows monism. However, in our case, the black hole may follow the dualism instead of the monism. Okay. And the second assumption is just this is comes from the quantum mechanics. Namely, the purification pattern of the black hole B exists in the outside. Outside is written in B bar in this my talk, and namely B plus B minus B bar is in a pure state. This is just a notion of the purification. If we want, one could regard B plus represents this region, which includes a singularity in the extended classical space-time, and B minus may represent this second asymptotically flat region if you want. Okay, so what is our main idea? Just we assume two things. Then the argument is the following: the area of the black hole is proportional to coherent information rather than simple entropy. This is our argument. Here, the coherent information is a B has a direction actually, but we take that coherent information from the outside to the positive energy particle inside the black hole. Therefore, we modify this Wittgenstein-Hawking equation. As I said, this coherent information related with entanglement. This is because that this coherent information becomes positive only when then conditional entropy becomes negative, which happens only in the case of the quantum regime. Therefore, in our formulation, black holes seem to be stored entanglement between outside and the inside. The size of the black hole may be associated with the size of entanglement between inside and outside. Actually, that's why we chose this type of formula, which comes from the following fact. As I said, black hole purification should exist outside. Therefore, the B plus B minus B bar is in a pure state. In this case, we have this type of mathematical relationship. Therefore, we can rephrase this formula in this form, this simple form. In this case, the area over 4 is equivalent to the positive energy part of the black hole entropy minus entropy of the negative energy part of the black hole. Therefore, our just the contribution is very small. Just we add this term here. Then the first term is just rephrasing this original Wittgenstein-Hawking equation. To keep the Hawking equation picture as it is, we added this term. This is similar to the Maxwell did for what Maxwell did to establish Maxwell equation. We just add this term. Please notice that this definition looks pretty good because this quantity sometimes related with entanglement. Therefore, it looks like area may be defined by correlation between the inside and the outside. However, this definition is defined by local, namely, once we understand the description of the black hole as a density operator, we can calculate its area. Therefore, this area should be determined independent of the state of the outside. Therefore, this type of nice property is satisfied. In addition, that as I said, the second term, as long as we consider the process where there is no exchange, there is no Hawking radiation. In such a case, the second term always there. Therefore, this formula is reduced into the original Wittgenstein-Hawking formula. And in addition, that this is consistent with the original Hawking pair creation picture. I finally mentioned about this one. This is pretty simple, just like we considered some Gedanken experiment where the black hole be absorb a system positive energy particle from the outside, while black hole emits a Hawking pair H plus H minus. Then the change of the black hole energy and the coherent information are described like this form. Because in this process, black hole receives a positive energy particle from the outside. On the other hand, black hole emits a Hawking radiation to the outside. Therefore, the change of the mass is described by this form. And at the same time, this black hole receives a positive energy particle from the outside. On the other hand, also black hole receives a negative energy particle through the Hawking pair creation. Therefore, this pair change. This is a change of the coherent information. Let's imagine the situation where the system A is in a perfectly copy of the Hawking radiation H+. In this case, for example, if the system A is in the thermal state with a Hawking temperature TB, in this case, EA, energy of this particle A and the particle H+ is the same. Of course, both are given state, therefore the entropy is the same. Therefore, the change of the mass and the change of the coherent information is there. Therefore, either from our new modified area law or either from the first law of black hole mechanics, we can conclude the area change doesn't occur. Therefore, this consideration is like a black hole be surrounded by thermal system with a Hawking temperature TB is exactly an equilibrium state, which is consistent with Hawking's original argument. However, that for such a system, we just consider small perturbations, such as for the equilibrium state. Then in this case, let us consider the change of the coherent information. In this case, of course, this S and SH becomes a change of the entropy of the system. In this case, system A and H+ is a given state. Therefore, this SA and SH follow the thermodynamic relationship. Therefore, we can replace change of the coherent information by using the change of the mass according to this expression. Then let us assume that our equation holds. In this case, the total equation is actually reproduce the first law of the black hole mechanics. Therefore, if we assume that the coherent information is AB/4, in this case, that the total equation reproduces the first law of the black hole mechanics. Therefore, it's okay. Therefore, without changing the Hawking's pair creation picture, we can reproduce. We can bypass the puzzle I have mentioned in this talk. I also, as I said, the coherent information has a clear operational meaning. Like coherent information represents how many qubits are distributed between the outside Alice and Bob. In this situation, if we apply the quantum state merging in this situation, this suggests that the AB/4 represent the if we consider the coherent version of the quantum state merging protocol, in such a case, if this formula is correct, then AB/4 represents the size of maximally entanglement distillable between the usual positive energy particle inside the hole and its outside by a process at the outside, which does not change the area. Therefore, if this formula was correct, area/4 clearly represents how many distillable entanglement exist between the inside the hole and the outside. Okay, and I will briefly mention about the information loss paradox, but this is not so pretty different situation. So I want to just mention, but our formula is free from the information loss paradox. Normally, the information loss paradox starts from saying like our universe starts in a pure state. Therefore, the total system is a pure state, and the entropy of such a system itself, namely our entropy of our universe itself, starts from there. Then we have one black hole, one big black hole, Hawking radiation start. At some point, black hole disappear. As a result, our universe is fulfilled by thermal radiation only. As a result, if the black hole has no entropy, in such a case, area of the black hole is there. Besides that, however, our universe is now fulfilled by thermal radiation. Therefore, the entropy of our universe becomes non-zero, which is contradictory with the unitarity of the quantum mechanics. This is an information loss paradox normally explained in our community. And however, as I said, this story based on regarding a black hole is composed of the monotonic particle. But in our case, as I said, black hole is composed by not only positive energy particle, but also negative energy particle. Therefore, perfectly different. Therefore, our protocol is our proposal is free from the information loss paradox, and we also free from the firewall paradox, because the firewall paradox appear when we consider the page time or pages formulation for black hole physics. However, in our case, as I said, pages also regard our universe is made by radiation and Hall. Hall and radiation compose a single pure set. But in our case, black hole is composed of two systems plus radiation. Therefore, in our formulation, we regard the black hole and radiation is composed of tripartite system. Therefore, pretty different. Therefore, the page situation is pretty different from our formulation because in our case, in some sense, a tripartite system. And maybe which is related with Takane-san's question, if we assume that this, even if we change this formula into this formula, maybe from the quantum information theoretical viewpoint, there is no problem even if this type of generalized second law holds. But this is just a naive formulation. We cannot derive directly, but from naive notion, even if we replace the formula for area law, namely original formula based on the area over 4 is the entropy, but we added additional term. However, that still this type of generalized second law could hold even from the quantum mechanical viewpoint. There is no paradox even if this generalized second law holds. Okay, maybe I'm consumed, and therefore finally I just briefly mentioned like so far we have discussed only on the Schwarzschild black hole. However, this formula looks okay even for any stationary black hole which has a first law of the black hole mechanics. This is because that maybe even if we want to generalize the Schwarzschild from Schwarzschild black hole into general black hole, in such a case we just need to replace the mode frequency omega into this type of form according to Hawking's paper. Just by borrowing such a replacement, we can show that maybe our formula looks hold even for any stationary black hole, including Kerr or charged black holes. Okay, therefore this is my talk, and therefore the final message of my talk is if the Bekenstein-Hawking area law is allowed to be modified a little bit, we may not need to change Hawking's pair creation picture. In this case, that we just added second term in the original formula. In this formula, the negative energy particles produced by Hawking radiation behave as if they have a negative entropy. Thank you for your attention.
Thank you very much. So could you show a slide in the review part of the black hole physics? So especially you shown a Penrose diagram which show the emission of the particle of Hawking radiation.
Hawking's paper one?
Yeah, so Penrose diagram.
Penrose diagram.
Depicted.
Yeah. Here. Yeah, this is just a. Okay, go ahead. This one, okay.
No,
Not this
more previous
previous.
slide. Maybe at
review part. This
that part.
Okay.
So you have a Penrose diagram in this slide, and H minus is a partner particle of the Hawking particle H plus. Then, so you said that H minus is a negative energy particle. Why this is a negative energy particle?
This is comes from the general relativity thing. Like we here that we regard the energy represents the energy at infinity. Okay, energy at
Infinity means H plus goes to now future infinity, but H minus goes to the singularity.
I want to say that like all the picture is based on assuming that this picture is given by the observer standing at the future infinity.
Okay, then so H minus is covered by the horizon. So the outside observer cannot see H minus.
Indeed.
But if you use traditional quantum field theory in a curved spacetime, then H minus does not have a negative energy. You may be confused. So we have another mode. So in this level, if the H plus mode is very close to the horizon, then you can compute the expectation value of energy density by using the traditional scheme of the quantum field theory, then you notice that the energy density does not have the positive or negative value. So when H minus takes positive value density energy, it's just arrive at a few times of black hole radius. Then, so the spatial curvature gives the positive energy. Then H plus becomes the near part. So near horizon, H plus is just a virtual particle, just a quantum fluctuation with zero energy. Similarly, H minus has also zero point energy near horizon. But when H plus exchange the particle mode, which go into the horizon mode, this is not H minus, but they extend the energy. Then H plus becomes the real particle with positive energy, and then the extensive mode has a negative energy, which propagates to with a negative energy outside of horizon. This is not H minus, okay? But H minus is a partner. Yes, I agree. But H minus does not carry a negative energy itself. So I'm wondering, so this is your start point. So H minus has negative energy, right? But this assumption is not correct, I think.
Yeah, actually, we borrowed. I'm not so specialist for black hole physics. So actually, I confess that I'm not specialist for quantum physics over curved spacetime. And but I just our formulation is based on the formulation given in the review paper given by Tohoft. And of course, that maybe such a review paper, and so maybe wrong. And but we just assume that Tohoft's formulation. Okay, I need to skip this one. I just show the difference. What kind of Hawking's picture is adopted in my talk? This is written this review, old review paper 96. We just follow that formulation given in this paper. And so, of course, maybe other formulation could be possible, but
No. So this Penrose diagram, you have H minus in the top of the diagram, but this H minus propagate to the lower side of the left side of this Penrose diagram to
in this
upper side.
Yeah.
So the trajectory is just light trajectory, which starts on the left side to right side, and which is covered by the horizon. Then you can compute the energy density. Then H minus does not have negative energy.
But
So you may think so. H minus belongs to the left side region. Then so you may think H minus has a negative energy.
But Lorentz boost becomes minus H bar omega A daga A or something.
Yeah, but the energy, the sign of energy should be defined by the thermodynamics.
Okay.
So you want to consider the black hole thermodynamics. Then inside in the region B minus.
But to be honest, in our formulation, we don't.
Time should be ordinary direction.
Yeah, actually, but as I said, such a notion of the negative energy particle is needed only when that divided system only. As you can notice that actually we do not use that this particle should be negative energy particle. Like this particle should be different from the particle which thrown from the outside. This is the only assumption because this energy conservation law is based only on what kind of particle goes to the black hole and what kind of positive energy particle goes out. Therefore, we do not explicitly assume that H minus should be negative particle, energy particle.
I'm worried about, so you studied the motivation. So negative energy absorbs the black hole, then the event horizon shrink. So because the roots of the energy on mass. So
in the case of energy conservation law is anyway, and first law of the black hole mechanics, we do not need to use a negative energy particle, right? Because the fact that someone receives a positive energy at the future infinity means that the decrease of the mass of the hole.
Also, You mean, so you do not
Just we
assume,
just
you
use
do
the
not
pure
assume the
state.
partner of the Hawking particle does not need carrying a negative energy.
Actually,
So
that
in the
theoretical-
first part, you stress the point, but we do not need
yes, actually,
postulate.
yeah.
The partner should not have a negative
We just
energy.
use it, just a purification partner goes into the black hole.
But you assume that delta
Yeah.
AB should be decreased.
This
So
one, this one can be derived by using the first law of the black hole mechanics, right?
First law.
Without assuming what kind of property is held by
Yes.
H minus. Like
Yeah.
just we assume that somebody receive energy at the future infinity.
Mhm.
If we believe that the energy conservation law for the energy at infinity, in such a case that the mass of the black hole should decrease according to first law for black hole mechanics, then area decrease without assuming that H minus the energy spectrum.
Okay.
Yeah.
So you do not need to assume the H minus is a negative energy part.
Yeah, just like a
Okay.
name of the
Okay.
particle.
So
H
you
minus. Yeah.
you can eliminate the condition.
Yeah,
H
you-
minus can be positive energy or zero energy.
Yeah, anything is fine.
Okay.
Just like we want to differentiate such a purification partner of the Hawking pair as a particle which fallen outside the black hole, like a particle considered in the Bekenstein-Gedanken experiment. That's it.
But you do not need any existence of a negative energy flux outside the horizon, right? So
That's why
when
we assume that
we compute such an energy flux outside the horizon, then we may have such a negative energy flux outside the horizon, which is outside the horizon. Okay, but such a negative flux does not play any role in your argument, right? We do not need such a negative energy flux outside of horizon in your argument, right? Okay.
Okay.
There is the coffee break. to continue. If there are other questions or comments. From home, anyone? Okay. Okay, so if not, let's thank the speaker again.